AI is quietly crossing a threshold. It can now persuade people better than skilled humans, and it can do it with dense, fact-heavy arguments rather than charisma. At the same time, video models are breaking past the old quadratic cost wall, and low-bit training is being rethought from the geometry up. The pattern is clear, better reasoning at lower cost across text, video, and pre-training. Keep watching, because the details show where today's AI systems are getting sharper, faster, and more dangerous to underestimate. Let's explore the first paper. AI systems out-persuade expert humans. This pre-registered Oxford and UK AI Security Institute study shows that frontier conversational AI can out-persuade elite humans in live text debates. Across 18,978 conversations from 6,923 people, AI systems including Claude Opus 4.1 and 4.6, ChatGPT 4.0, GPT-5, 4, Grok 4.2, and Gemini 2.5 Pro beat random laypeople by 8.2 percentage points, tournament-selected laypeople by 5.6 points, elite debaters by 4.6 points, and professional canvassers by 5.9 points on post-conversation attitude change. In Study 2, coaching elite debaters increased their output by 19% more words and 54% more fact-checkable claims, but only raised persuasiveness by 1 point. The gap vanished only when AI was throttled to human throughput, with constrained AI limited to 51 words and 92 seconds per reply, matching elite debaters. Mechanistically, persuasive impact tracked fact density tightly. Unconstrained AI averaged about 37 fact-checkable claims per conversation versus about 12 under the constraint, and the overall relationship between facts and impact reached R2 equals 0.89. The advantage also generalized beyond attitudes. In a real money donation task to save the children, Claude Opus 4.6 beat professional canvassers by 10.8 points of a £1 bonus, raising both the share who donated and the amount donated among donors. The paper's core claim is that AI's edge comes less from charisma than from faster, denser information delivery. Let's explore the second paper, Linear Scaling Video VLMs for Long Video Understanding. StateKV from Stanford University is an inference time method for pre-trained video vision language models that linearizes long video prefill without fine-tuning or architecture changes. Instead of letting every new frame attend to the entire past, it maintains 2 KV caches per layer, a fixed capacity importance-based temporal state for cross-frame context, and a detailed full cache for final decoding, which reduces video prefill complexity from quadratic to linear in frame count. The paper's mechanistic analysis on 16 long videos from the Video MME training split shows that historical attention is highly concentrated. The top 4096 historical tokens capture 0.93 of historical attention mass for intern VL3, 1B, 2B, 8B, and the incremental candidate pool recovers the next oracle state with weighted recall of 0.96, 0.97, and 0.96 at B equals 256. On 3 benchmarks, Video MME, MLVU, and OVO bench StateKV, with B equals 4096, stays close to full self-attention and consistently outperforms ReKV's 1.6 frame sliding window. For example, on intern VL38, B, it reaches 62.52% on Video MME versus 64.19% for full self-attention and 54.56% for ReKV. The compute frontier is especially strong. StateKV, 8B at B equals 4096, achieves 62.5%. Video MME accuracy at similar flops to full SA, 1B, and the authors report that the larger StateKV model becomes compute favorable beyond about 1,800 frames. Let's explore the third paper, Rethinking Shrinkage Bias in LLM FP4, Pre-training Geometric Origin, Systemic Impact, and UFP4 Recipe. This Ant Group Ling Team paper argues that the default FP4 training choice in NVIDIA Blackwell, Rubin class, and AMD MI350 style recipes, E2M1, has a geometric flaw. Its non-uniform RTNE bins induce shrinkage bias, a systematic negative rounding error that compounds multiplicatively across layers. The authors show that random Hadamard transform, which is used to improve bucket utilization, can actually worsen E2M1 because it pushes tensor mass into E2M1's most asymmetric bins turning outlier mitigation into local resolution failure. They then introduced UFP4, a uniform 4-bit recipe built on E1, M2, INT4 style grids, applying RHT to all three training, GEMS, FPROP, DGRAD, and WGRAD while keeping stochastic rounding only on DY. On dense 1, 5B, Mo 7, 9B, and Mo 124B. Long-run pre-training UFP4 stays closer to BF16, reducing latest 1000 step BF16, relative loss error from 1.257% to 0.9673%, from 2.3596% to 1.8469%, and from 1.7308% to 1.3863%, respectively. An ablation on dense 1. 5B shows full RHT plus SR is best, improving mean LM loss by 0.01123 over no RHT, and fused RHT plus quantization adds only about 1.06x to 1.07x latency over standalone quantization. The paper's central claim is that future accelerators should treat E1, M2, INT4 style uniform 4-bit grids as first-class training primitives, not just E2, M1. That's a wrap on today's AI paper highlights. Thanks for watching.